Hello learners, welcome back. I am Rajat Tiwari, lecturer, University Teaching Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai, and your subject matter expert for this course. In today's session, we will be diving into the intricacies of leveling, where we will be focusing on sensitivity of level tube, inverted staff, difficulties and errors in leveling. We will explore how the sensitivity of the level tube impacts the accuracy of your measurement, the correct usage of an inverted staff in specific situations, and the common difficulties and errors encountered during leveling operations. In this session, we will be discussing firstly the sensitivity of bubble tube, then the use of inverted staff, then the difficulties in leveling operation, and lastly the errors in leveling. So, before sensitivity, we have to understand what is level tube. The level tube, which is also referred to as bubble tube, spirit level or level, is used in most surveying instrument to determine the direction of gravity. It is a sealed glass tube with both ends closed and its interior is ground to form a longitudinal circular curve. The tube is nearly filled with a sensitive liquid such as alcohol or ether, leaving just enough space to create a bubble. The liquid used must be quick to respond, resistant to freezing, and stable under normal temperature variations. Purified synthetic alcohol is considered the best choice for this purpose, as you can see in this diagram. Now, the sensitivity of a level tube depends on the following. Firstly, the radius of curvature of the internal surface of the tube. Larger the radius, greater is the sensitiveness. Secondly, the diameter of the level tube. Larger the diameter, greater is the sensitiveness. Thirdly, the length of the vapor bubble. Larger the length, greater is the sensitiveness. Then the viscosity and the surface tension of the liquid. Lesser the viscosity, more is the sensitiveness. And lastly, the smoothness of the finish of the internal surface of the tube. So, greater the smoothness, more will be your sensitivity. Now, how can we measure this sensitivity? We will do step by step process so that how we can measure the sensitivity. Firstly, we will fix 2 points at a known distance apart, say 100 meter. In the next step, we will set up and level the instrument as shown in this diagram at O. We will take the reading on a staff held vertical at station C. Now, by turning the foot screw beneath the telescope, we will move the bubble to end divisions, and next we will read the staff again, and the last step we will find the difference in two staff readings. So, the sensitivity alpha is equal to S by D, which is equal to N multiplied by 1 upon R, where alpha is the angle between the line of sight in radians. D is equal to distance of the instrument from the staff. N is equal to number of divisions through which the bubble is moved, and R is the radius of curvature of tube. S will be your staff intercept. L will be your length of one division of bubble tube, which is usually 2 mm. From the above equation, we can write R as NLD whole divided by S, and 1 upon R can be written as S upon ND. So, alpha dash, that is sensitivity, can be written as 1 upon R, which will be equal to S upon ND multiplied by 206265, which will be in your seconds, where alpha dash is your sensitivity of bubble tube. Now, let us take some examples to make it more clear. So, we have to find the radius of longitudinal curvature of the bubble tube on which the divisions are 2 mm long. If the angular value of one division is 30 second, now we know R is equal to L upon alpha. Okay. So, L have been given as 2 mm. So, we can convert it into meter as 0.002 meter. Alpha can be calculated as 30 divided by 206265 radians. Now we can calculate R, which will be equal to 0.002 multiplied by 206265 divided by 30, that is L by alpha, which will give your result as 13.75 meter. So, radius of longitudinal curve will be 13.75 meter. Now, in the second question, it has been given the bubble tube of a level has a sensitiveness of 30 per 2 mm division. We have to find the error in staff reading on a vertically held staff at a distance of 150 meter caused by a bubble 2 divisions out of the center. Now, as we know, sensitivity is equal to S upon Nd multiplied by 206265. So, S can be written as alpha and D divided by 206265. So, we know the value of alpha as 30 and that is number of divisions are 2 and D has been given as 150 meter. So, we will put these value in the equation and get the answer as 0.0436 meter. So, the error will be in the staff reading will be 0.0436 meter. In the next question, it has been given as that bringing the bubble center, the reading taken on a staff 200 meter from the instrument was 2856 meter. The bubble was then moved 5 divisions out of center and the staff reading observed was 2.806 meter. If the length of one division of the bubble is 2 mm, we have to calculate the radius of curvature of the bubble tube and also the angular value of one division of the bubble. So, in the solution part, that staff intercept S for a deviation of 5 division of the bubble will be equal to 2.856 minus 2.806, which will be equal to 0.050 meter. Firstly, the radius of curvature R can be calculated as N small d capital D divided by S. Here N will be equal to 5, small d is 2 mm, capital D is 200 meter. So, R can be calculated as 5 multiplied by 2 multiplied by 200 whole divided by 1000 multiplied by 0.050 meters, which will result in 40 meters. Thirdly, the sensitivity of bubble alpha dash can be calculated as S upon Nd multiplied by 206265 in seconds. So, as you know, S is 0.05, N is 5 and capital D is 200. So, we will put this value in the equation and we will find out the value as 10.31 seconds. In the next question, if the bubble tube of a level has a sensitiveness of 30 minutes per 2 mm division, we have to find the error in staff reading on a vertically held staff at a distance of 150 meter caused by the bubble 2.5 divisions out of center. So, the angular value of one division of 2 mm length alpha dash can be equal to S upon Nd into 206265, as you know the equation. So, N is given as 2.5 and the capital D has been given as 150 meter. So, we will put these values and find the staff intercept as alpha dash Nd divided by 206265. Alpha dash is 30, N is 2.5, D is 150 meter. We will put these values and we will find the staff intercept as 0.055 meters. Now, we will move on to next topic, that is use of inverted staff. So, when the point whose elevation needs to be determined is significantly above the line of sight, such as a projection from a building face or the underside of beams, girders or arches, the staff is placed upside down with its zero end touching the point. The staff reading is then taken in the usual way. To make it easier to identify, this reading is recorded in the leveling book with a minus sign. For example, during a leveling operation, inverted sides were taken at a point B, C, D and E as shown in the figure. The elevation of this point can be determined by simply adding the staff readings to the height of the instrument. The method of recording and calculating this level is as shown. Here, field level book has been shown where station, backside, intermediate side, foreside and the height of instrument and all the points RL have been shown with the use of inverted staff. Now, we will take some examples to clarify it more. So, we have to find the height of a T-beam above the floor level. The RL of the floor is 100.855 meter and the staff reading on the floor is 2.055 meter. The reading on a staff held upside down against the underside of the beam is 3.565 meter. So, firstly, the reduced level of plane of collimation we will find out. The height of instrument will be equal to 100.855, that is the RL of the floor, plus 2.055, that is the staff reading on the floor. We will add both of them to get the height of instrument, which will result in 102.910 meters. Now, the RL of the underside of the T-beam will be 102.910, that is the height of the instrument, plus 3.565, that is the reading on staff held upside down against the underside of the beam. We will add both of them to get it as 106.475 meter. Hence, the height of the T-beam above the floor level will get by subtracting both these values, that is 106.475 minus 100.855, which will result in 5.62 meters. So, the height of T-beam will be 5.62 meter above the floor level. Moving on to the next example, the reduced level of a factory floor is 30 meters and the staff reading on the floor is 1.40 meters. The staff reading when held inverted with the bottom touching the T-beam of the roof is 3.67 meter. We have to find the height of beam above the floor. So, it's same question as the previous one. So, RL of the factory floor is 30 meters, staff reading on the floor is 1.4 meters and the inverted staff reading has been given as 3.67 meters. So, the height of T-beam above the floor will be, we will add the staff reading on the floor and the inverted staff reading, will get the height of T-beam above the floor, that is 1.40 plus 3.67, that will be equal to 5.07 meters. Now, we will move on to the difficulties during the leveling operations. So, during leveling operations several changes can arise, which includes firstly the verticality of the level staff on slopes. Ensuring that a level staff is vertical on slopes can be difficult. To check verticality, a plumb bob should be used. When ascending a hill, the backside reading will be taken near the top of the staff, while the foreside reading will be taken near the bottom as shown in the figure A. The opposite occurs when descending a hill as shown in the figure B. This can make it challenging to read the staff near its base. Now, to address this, we have to place the staff close to the instrument during foresight when ascending and during backside when descending. This may result in unequal backside and foresight distances, which will introduce errors from imperfect instrument adjustment. To minimize this, ensure the instrument is in perfect condition. Another approach is to position the instrument off the line of levels and take zigzag readings, which is particularly helpful for avoiding short sights. Now, the next difficulty is the leveling across a summit or a hollow. When leveling across a summit or a hollow, it is important to carefully select the instrument position. Placing the level on one side of the summit or hollow can save time and effort. Near the summit, set the level high enough and near the hollow, set it low enough to accommodate all necessary observations. Next difficulty will be your taking observation above the line of sight. To observe a point above the line of sight, we have to hold the level staff inverted and take the reading. This process has been discussed in the previous slides. Now, next one is the leveling across ponds and lakes. So, when a pond or lake is too wide or sight across, drive two pegs say A and B on opposite sides, flush with water surface as shown in the figure. Set the level on one side and take reading on staff at A. The reduced level of peg A and thus the water surface is known. Now we will shift the level to the other side and take a reading at B. Since the water surface is level and the reduced level of peg B will match that of A, by adding the reading at B to the reduced level of A, the height of the instrument is determined, allowing the leveling to continue. Next is the leveling across a river. To level across a river, we will use the method of reciprocal leveling, which has been discussed in the previous session. Next is the leveling past a wall. So, if a wall obstructs the leveling path, that we will determine the reduced level of wall's top before continuing on the other side. If the wall's height above the line of sight is less than the staff length, we will hold the staff inverted with its zero end on the wall's top and take the reading. Adding this reading to the height of instrument gives the RL of the wall's top. Next, we will move the instrument to the other side and hold the staff inverted again and subtract the reading from the wall's reduced level to find the new height of instrument, and then we can continue leveling. If the wall is too high to use an inverted staff, we will use a tape to measure the height from the line of sight marked as A on the wall to the top. We will add this height to the height of instrument to get the wall's reduced level. Nextly, we will move the instrument to the other side and mark where the new line of sight strikes the wall, that is B, and measure the height from this mark to the top. Next, we will subtract the height from the wall's reduced level to get the new height of instrument, then continue leveling. So, next difficulty is about when the staff is too close to the level. So, if the staff is too close to the level, the graduation may not be clearly visible. To overcome this, the surveyor can move a piece of paper along the staff until the edge of the paper aligns the line of collimation. The reading at the paper's edge will be the required observation. Now, we will move on to the next topic, or the last topic of today's session will be your errors in leveling. Errors in leveling may be categorized into the following three heads. First one is personal error, second one is error due to natural causes, third one is instrument errors. We will discuss each error one by one. First one is the personal errors. So, the personal errors includes firstly the error in sighting, next is the error in manipulation, next is the error in reading the staff, and lastly the error in recording and computation. Now, we will discuss firstly error in sighting. This error is caused when it is difficult to see the exact coincidence of the crosshairs and the staff graduation. This may be either due to long sights or due to coarseness of the crosshairs and the staff. Sometimes atmospheric conditions also cause an error in sighting. This error is accidental and may be classified as compensative. Next error is error in manipulation. These include the errors due to the following reasons. Firstly, carelessly setting up the level. The instrument should be set up on firm ground and carefully leveled. Neither the telescope nor the tripod should be touched while taking readings. Next is the imperfect focusing of eyepiece and objective. So, to eliminate these errors, the eyepiece must be moved in or out till the crosshairs are distinctly visible against a white paper. The parallax should also be completely removed by properly focusing the object glass before taking every reading. Next is the bubble not being central at the time of taking readings. So, when the bubble is exactly central, the vertical axis is truly vertical and the horizontal axis of the telescope becomes horizontal. If the bubble is not central, the horizontal axis of the telescope gets inclined, which affects the staff reading. The error is more for long sights and less for short sights. To avoid this error, the observer should develop a habit to check the bubble before and after taking readings. Next is the non-verticality of the staff. So, when a plumb bob isn't attached to a leveling staff, it can be challenging to ensure that the staff is vertical in the line of sight. If the staff is tilted, the readings will always be too high. The error increases with large staff readings for the same angle of tilt and decreases with smaller readings. Therefore, when taking larger readings, it is crucial to carefully verify the staff's verticality. In typical leveling procedures, the staff person can be instructed to move the staff slightly towards or away from the level to find the minimum reading. To check for non-verticality in the direction perpendicular to the line of sight, the use of two vertical crosshairs is effective. Additionally, the horizontal crosshair will not align with graduations on the staff unless the staff is vertical in transverse direction. Next error is error in the reading staff. These errors are generally committed by beginner and are firstly reading the staff upwards instead of downwards. Next is reading against the top or bottom hair instead of central hair. Next is the concentrating the attention on the decimal part of the reading and reading the whole meter wrongly. Next is reading the inverted staff as a vertically held staff. Next error is error in recording and computation. So, common mistakes in recording will include firstly placing a reading in the incorrect column such as entering a backside reading in the intermediate side reading or foresight reading or foresight column or vice versa. Nextly, reversing the digits in the reading, for example, writing 2.654 instead of 2.456. Here the digits have been reversed. Next, failing to record a reading. We can also fail to record a reading also. Next is misinterpreting the numerical value of a reading announced by a level operator. Next is recording an inverted staff reading without noting the negative sign. And lastly, we can also adding a foresight reading instead of subtracting it, or mistakenly subtracting a backside reading instead of adding it. Next error is error due to natural causes. These errors are influenced by natural factors and includes firstly the errors due to curvature. The curvature of the earth's surface causes a reduction in the elevation of a station, and this effect is directly proportional to the square of the horizontal distance between the staff position and the observation point. To obtain an accurate reading, the correction for curvature must be subtracted from the observed staff reading. In ordinary leveling, the error due to curvature is typically negligible, that is only about 0.003 meter for a 300 meter site. So, for detailed information on calculating curvature correction has already been discussed in detail in the previous sessions. Next is the error due to refraction. Refraction has an opposite effect to curvature. as it increases the elevation of the station. Like curvature, the error due to refraction is directly proportional to the square of the horizontal distance from the station to the level. However, for short distances, this error is generally negligible and can be ignored in routine leveling. For more information on calculating the correction for refraction has been discussed in the previous session. Next is error due to wind and sun. Strong wind make it difficult to keep the staff vertical, leading to incorrect reading due to non-verticality. Wind can also cause vibrations in the instrument, making it challenging to keep the level tube bubble centered. In windy condition, it is advisable to pause the work to protect the level with an umbrella and keep the staff readings minimal. The sun can also cause issues by shining on the objective lens, so it is recommended to shield the lens with an umbrella. Additionally, temperature changes due to sunlight can slightly alter the length of the staff, though this effect is negligible in routine leveling. Next is the instrumental errors. Instrumental error arise from the following causes. First is imperfect adjustment of the level. In a well adjusted level, the line of collimation should remain horizontal when the bubble in the level tube is centered. If the level is not properly adjusted, the line of collimation may incline either upward or downward, leading to inaccurate readings. The error can be minimized if the backside and foreside distances are kept equal, as in case of fly leveling. However, in the case of intermediate sides where the distance vary, the readings can be significantly affected. On steep slopes where the backsides are either longer or shorter than the foreside, the error can accumulate. It is important to note that the error due to improper level adjustment are common and serious. The level should be carefully tested and adjusted before use, and care should be taken to ensure that backside and foreside distances are equal. Next is the defective level tube. So, a sluggish bubble in the level tube may stay centered even if the bubble axis is not horizontal, while an overly sensitive bubble can require considerable time to center. Irregular curvature of the bubble tube is also significant defect. However, the effect of a defective level tube can be mitigated if the sides are kept equal. Next is the unstable tripod. A shaky tripod leads to instrument instability, making it difficult to take accurate readings. Time is wasted trying to stabilize the instrument. Before taking the observation, all bolts, nuts and screws on the tripod should be securely tightened. A good way to test the tripod stability is to twist one of its legs after taking a reading and then release it. If the reading changes, the tripod is not stable. Next is the incorrect staff graduations. If the staff graduations are inaccurate, errors can occur. However, in ordinary leveling, this error is usually negligible because the readings are typically only taken to the nearest of 0.005 meters. In precise leveling, the graduation should be checked against an invert tape under magnification to ensure accuracy. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.